shown generally by revolving loops around the cassette. We have approximate the volume using cylinder. Volume can be found using velocity equals pi r squared times height, and then apply r knowledge for the limits integral to generate an expression.
Okay, so I want to stop you right there for a second. So when we first started our journey of revolution, and this was just a couple of days ago, right? What we did is we said, okay, if I'm going to take this region over here and I want to revolve it around the x-axis, we have to go down the path that Riemann went down first. And what did Riemann tell us to do? Right, we'd make a whole bunch of little rectangles, but really I'm just going to focus in on this one little rectangle over here. And this rectangle has a height. The height of this rectangle is f of x. This rectangle has a thickness. How thick? Oh, how thick? Dx. This is going to be dx, or I'm going to go with delta x right now. We would first find the area of the rectangle, and then the next thing that you do, if I imagine this guy spinning around the x-axis, right, what we have to do is think about what happens when I take my rectangle and I spin it. What's the shape? Cylinder. We get the volume of a cylinder. And you guys know that the volume of a cylinder is pi times r squared times the height. For us specifically, f of x is your radius. It goes from the axis of rotation up to the curve, so this is the r. The delta x is the height, it's the thickness. I like to think of this as like the volume of a slice. So the volume of my slice is pi times f of x squared times delta x. That's the volume when one rectangle gets spun around the x-axis. Everybody okay? I don't want the volume of a slice though. What I want is volume of a solid. I want to take all those slices, all the chops, and add them all up. Well, how do I do that in calculus?
Pi times definite integral.
Right, we wind up doing a definite integral from a to b of pi times f of x squared times dx. You think first about a slice, and then you think about the solid, because this really what's hiding in here is you did this infinite sum of that limit as n approaches infinity, pi f of x sub I squared delta x, and then you get this volume of a solid. Questions so far? Hi, Homer. Friends, we're okay? This idea of first find the volume of the slice, then find volume of the solid is the only new piece. That's where we're going. Anthony, you look like you have a question. No? All right, Brian, can you pick it up from here?
Yeah. We have also modified this integral expression so that we can find the volume of solids formed by revolving around the y-axis, any horizontal line and any vertical line. We have also explored three-dimensional objects which are composed of more than one function being revolved around the set axis. The key to solving all of these problems has been to think about the representative rectangles in the cylinders, washers that are generated.
Okay, perfect. So if you understand that, like, behind the scenes, we've got this formula here, that this is really all that you need to do for your volume of revolution. Sometimes I'm going to have you revolve around a line that's lower or one that's up higher. Sometimes it's hollow, sometimes it's solid. You adjust a little bit, but really it's just this same formula again and again and again. We're okay? Good. All right, Rogelio, Lucia, can you pick up from there?
Where are we going? Now we move into a different class of solids. For the next few days we will explore solids whose cross sections are squares, rectangles, semicircles, ellipses, isosceles, right triangles, and a variety of friendly geometric shapes. The process will be the same.
Yeah, you can keep going.
Determine how you would approximate the true volume using thick cross methods.
Thick cross sections?
Thick cross sections, my bad. Use limits and properties of the integral to generate the appropriate definite integral. Attack the integral expression with either your integration skills or your calculator skills to generate the true volume. Do the happy dance and high five your neighbor when you get the correct answer.
Slap your
Not slap them. Okay, So all of these shapes over here, number one, they are hard to come by real life objects that I can bring into the classroom and show you. So, which is why I'm greatly appreciative of Carolina and what we get Henry and Eduardo and whoever made the shark and whoever did the Titanic, so that you can at least get some semblance of what these objects look like. Actually making these things is to make a real one is a very expensive process because it takes so much precision. Have any of you guys seen the 3D printers?
Oh yeah, these are cool.
Those can handle these objects. They're still not as precise because you're just looking at like melting plastic and all those things. But those 3D printers are sweet. If I can get my hands on one, we are going to get some real solids that I can like play around with.
You can afford it.
Ask for a better budget.
Exactly. That's got to be the key. All right. So what I want to do is let's take a gander at like the geometry of this. And Victoria, how do you feel about driving the Geometry Sketchpad program? Are you okay?
Yeah.
Yeah, you guys also don't get Geometry Sketchpad. Sorry.
We do have one.
I do.
Oh, I thought you
I
had
wait,
it
that's
up
how.
here.
Yeah, we're not going to do that. That's not really the point.
This is homework.
Press source to switch input.
That's gonna be you.
Okay, I'm waiting. What's going on here? Excellent. And now we switch.
See?
Okay. And what happened here? Is Mr. Link sabotaging me again?
Yeah.
He doesn't want me to be the best math teacher in the room, so he sabotages me.
I think they did some.
All right, there we go. Here it comes. All right, and I need my slices. And today is going to sound like a karate dojo. UI? DX? Okay, I'm so tired of seeing that visual. I want Geometry Sketchpad. Get me Geometry Sketchpad.
Take your time.
No, I hate wasting time, Chepe.
Lucio.
This is the thing you and I still don't seem to understand about each other.
Really? It's very easy. Just going too fast.
Oh, sorry. Oh my God, all the things were wrong.
Mr. Link
Valid.
sabotage.
No. Yeah, pressing. Superman.
All right, good. Victoria? There we go, good. Okay, so
Oh man.
here's how it's gonna work. Here's how these things are gonna work. This circle, it is not important, it is not special that this is a circle. The way these problems are gonna be set up, they define the base, they define the flat part for you, and then they'll say how you're making your slices. And when I say how you make the slices, I want you to show me with your arm which way you're gonna go. So if I said this is the x-axis and this is the y-axis, and you're making your slices perpendicular to the x-axis. Perpendicular to the x-axis, what does that look like? Perpendicular to the x-axis. So if I'm making my slice this way, think about my thickness of the slice. That thickness is, how's that thickness gonna be? Is it a dx thickness or a dy thickness? It's a dx? Okay, so perpendicular to the x-axis, show me perpendicular to the x-axis. Perpendicular to the x-axis is dx. Okay? Sometimes I'm going to say make your slices parallel to the x-axis. Show me parallel to the x-axis. Victoria, you okay there? You're looking... Wait, parallel to the x-axis. Parallel to the x-axis. Show me a chop parallel to the x-axis. Parallel to the x-axis, we're going this way, right? What kind of integral? If your slices are going this way, dy. You gotta say it that way, Jeffy. Okay? Maybe your slices are parallel to the y-axis. Show me parallel to the y-axis. Parallel to the y-axis. What kind of chop are you doing?
Seminole chop.
If you are doing parallel to the y-axis, this is dx. Your other option is I might say perpendicular to the y-axis. Perpendicular to the y-axis. Think y-axis, think perpendicular. What kind of chop is this?
Brisket chop.
dy. It's a dy kind of chop. All right. So we have our base. Now, here's what we're going to do so that you can get the three-dimensionalness of this. Victoria, I want you to click on the box where it says drop y-axis flat.
Wait, what? That's it?
Welcome the z-axis.
DZ.
We're not going to do DZ. Your x-axis is still horizontal. Your y-axis was the vertical, but imagine taking this board, ripping it off the wall, and laying it flat. That's what this y-axis diagonal is representing. And the thing that sticks straight up is the z-axis. Okay? So now we're looking at height. So Victoria, hit reset. There we go. So this is the shape. I'm always going to define the base shape in the XY plane. But we're going to drop it flat so that you can visualize this. X-axis stays horizontal, drop y-axis flat. There it goes, like boop. Z-axis points up. Now I'm going to have to tell you about the slices. I want to make slices that are squares with one side in the base. So if you could, Victoria, if you could show me 4 squares. See 4 squares? My squares are going from one side of the base all the way to the other side of the base. What direction are we making these slices? Are these dx slices or dy slices?
They're parallel to the y-axis, so it should be DX.
Here's my x-axis. I am making them, I heard parallel to the y-axis. Another way you could say parallel to the y-axis would be perpendicular to the x-axis, same idea. So you're slicing this way, these are going to be dx kinds of things, but they're squares. And the way I'm going to find the area of a square is say how long is the square, how tall is the square, find the area of the square, then take into account the thickness to make the slice, and then add up all those slices to get the volume. Big picture, we're kind of okay?
Yeah.
All right, good. Everybody else? Good. All right, Victoria, sweep one square. So we can see that one square going from one side of the circle all the way to the other side of the circle. It shouldn't be a surprise, I hope, that the circle gets... Okay, that was a surprise. The square is getting wider. Brian, why is it getting wider?
Because I think the radius is getting bigger. And it's smaller.
Be careful with the choice of the word radius. Because if this guy here, the base is a circle, the radius does not actually ever change on you.
The distance from each edge.
The distance from one side of the circle to the other side is increasing. Over here, it's pretty short. Gets bigger, 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 bigger. Square has to get bigger to make that gap. And now it starts to get shorter as we get to the end. Okay, Victoria, one more. I want you to hit create solid. So now what you're getting is like that wireframe shape. Right? Imagine all your slices. This is what the solid looks like.
That's cool.
It is kind of cool, huh? All right, Victoria, can you click on Show Solid?
Something like a Scooby-Doo.
So that's the object. This is what the thing would actually look like if we could make this in 3 dimensions.
Oh, this taco.
You see a taco?
It looks like the thing that you see when
Oh,
you spray.
I see it.
It looks like
All
when
right, I'm with
spray-
you. I'm with you on the taco.
A little Febreze spray that you
They chip it.
like the very top of the Febreze spray.
Oh, at the very top of the Febreze thing? And anybody else? Any other visuals out there?
Wait, so it wouldn't look like this, right? Like this, like a difference, like a big difference.
No, because these slices are squares. The slices you're looking at are right isosceles triangles.
Well, yeah, but like what I'm saying is like they wouldn't be like they're not like the heights aren't close to each other. Like there's like a big gap.
Well, this actually, you'd want to think about an infinite number of slices. It wouldn't be this boxy, choppy thing. It would be smooth to the touch. Okay? All right, and then if you click on +4 squares, Victoria, what we're going to see is this, with +4 squares, go down.
No.
It's on Show Solid.
not supposed to squares?
Yes.
Yeah, well, it still says show solid. So now we've got the solid wire frame. Like when I say, I've never seen the taco, but I get the taco now, and I get the Febreze thing. In my mind, I'm seeing like a bird cage.
Oh,
I see it.
eso va de little.
Maybe it's because of all like the little like wire slices there, but some bird cages like have that shape.
Ah.
And these squares run perfectly from one side to the other and up to the top, and that's going to be what's happening on the inside. Big picture, we're okay? All right, there are some other animations I could go through, but like this is really the big idea. What I want us to do is play around with this and see what happens. We'll go from there. Victoria, great job. If you could come on back and join the young men over here.
We're gonna get sent to war.
Okay.
All right. Let's do one together, and then you guys can sort of spin off and go at whatever pace is comfortable. The base of a solid is the region bounded by the graphs of y equals e to the negative x, y equals -1, x equals 0, and x equals 1. Each cross-section perpendicular to the x-axis is a square with one side in the xy plane. And I want to determine the volume of the solid. So we're gonna go all in. I'm always going to tell you about the base shape. I have to tell you about the base. So let's start with the base. What's that going to look like? What do we know about the base here?
There's one function which is y equals -1.
Yeah, that's
There's y equals -1, so that's horizontal line down here. Okay, what else is part of the base? We've got to build the base. We've got to build the flat thing. What else, Shepard?
a y equals e to the power negative.
Y equals e to the power of
Negative.
-x. So I'm going to continue to pick friendly shapes for you guys when we start building this base.
Friendship.
Y equals e to the -x. We've got y equals -1. We have x equals 0. Here's x equals 0. And we have x equals 1. This piece here is your base. Now, at no point am I asking you for area of the base. I'm also not asking you to spin the region. There's no words of revolution here. There's no spinning verbs. This is your base. What do you do with the base? What does the problem tell you to do?
Put squares.
Determine the volume of this.
I need squares. And what am I doing? Which way am I slicing?
Perpendicular to the x-axis.
Perpendicular to the x-axis. Just show me perpendicular to the x-axis. Which way? Perpendicular to the x-axis, we're going this way, right? What I'm saying by your slice, there's some imaginary, I can't see it, three-dimensional thing popping out of the board. But what I'm saying is that when I slice, which way?
Perpendicular.
Perpendicular to the x-axis. dx or dy?
Dx.
dx or dy if I'm going this way. Think about that rectangle, that little representative slice. Wouldn't you call that a dx? dx! Okay, I'm alone on that. I really miss Roger today. Okay, so here's my base. I'm slicing dx!
Yeah.
And yep, I'm so alone. And all of my slices are these squares. Right? I'm not going to make smaller squares and smaller squares. This isn't even like drawn to scale. But the idea is I have squares here, and squares here, and squares here, and squares here, and squares here. All the way through, it's squares that are popping out of the board. The visualization of this is the tricky part. Don't let that worry you. Everybody's okay with the base? So here's what I normally do. I say, okay, let me do a little slice here. And I'm going to call this slice right here L. That's how long this is. The thickness.
Dx or delta x.
Okay, I'm going to call it delta x. If you call it dx, that's fine too. I want to know about the volume of a slice. Not the solid, just a slice. So imagine, if you will, I'm going to take this little slice and I'm going to put it over here and say, okay, here's my slice. My slice is a square, and it's got a little bit of thickness. That's the only way we can really get volume here. The length is L, but this is a square, right?
So it's L squared.
So the height is L, and the thickness, this part here, is the delta x or the dx, and I'm going to use those interchangeably, so don't worry about it too terribly much. This is one slice. My little piece of paper that has some thickness coming out of the board, I'm just saying, let me put it over here and find the volume of this slice. That's the volume of the slice. Now what I need is volume of the solid. We'll take our lessons from Riemann and the way that we did area, and then the way that we did volumes of revolution. It's the same way we're going to handle these cross sections coming out of the board. If you know volume of the slice is L times dx or delta x, look at that, I'm already being sloppy. Then the way I get the volume of a solid, which means add up all my slices, trust your instincts here. We figured out how to do volume of a slice, volume of the solid.
Can we just do the sum of all those slices?
It's the sum of all those slices. It's that infinite sum over there, which gets us to an integral of L squared dx from A to B. That's your setup. That's not final answer. Why is it not the final answer?
What's your L?
Yeah, what's L? Another question to ask. What's A? What's B? Probably A and B are easy.
From 0, 1.
Right? If this is my base region, I start slicing at x equals 0. I stop slicing at x equals 1. We're okay that this is A and this is B? Okay. So my integral now is going to be an integral from 0 to 1. What I haven't heard yet, what we haven't had conversation about is L. Here's the beauty of L. L just represents how long the slice is. You guys know exactly how to figure out how long that slice is. How long is this little slice?
It's like the one and the top and
It's this guy up here, the top function,
minus the bottom.
minus the bottom function. So L is really e to the negative x, top guy, minus the bottom guy.
Plus 1.
Right, so really plus 1, but I'm going to write it this way, top minus bottom, so you can see it. Victoria, are you okay? Friends over here, are we okay? Anthony?
What about the pi?
What about the pi? There's no pi here.
Because you're not revolving it.
Because it's not a volume of revolution. We're not talking about circles anymore.
Oh.
Right? Think about your slice. Your slice is a square. The reason we had the pi is that my slices were cylinders before, and area of a cylinder, volume of a cylinder is pi r squared times thickness. Now you're thinking specifically about the slice. But same big idea. Okay. So I bet for most of you guys, finishing the problem off from here should be pretty good. Right? We're past new calculus. This is just old calculus to get some practice. So if you feel good, finish it off. I'm going to keep working this one out. So the integral from 0 to 1 e to the negative x plus 1 squared. Well, because of the square, I actually have to multiply this out. I might think about integration by substitution, but if I call u this e to the negative x plus 1, I don't have the derivative of the baby there, so I'm going to have to multiply this out. E to the negative x plus 1 times e to the negative x plus 1, I would be careful here. E to the negative 2x plus e to the negative x, oh, I'll have that twice, plus 1 with respect to x. Antiderivative of e to the negative 2x is negative a half. E to the negative 2x. Antiderivative of e to the negative x is negative e to the negative x, and I've got to double that. Plus the antiderivative of 1 is x. I'm going to look really carefully at your notation. Are you keeping that evaluation bar in there? Now just plug this stuff in. Negative a half e to the negative 2 minus 2 e to the negative 1 plus 1 minus, plug in the 0, negative a half e to the 0 minus 2 e to the 0 plus 0. And for the sake of getting good practice, I do want to simplify this all the way. So negative 1 over 2e squared minus 2 over e plus 1. 1 negative a half, it looks like plus a half. Negative 2 times that negative makes that plus 2. I think negative 1 over 2e squared minus 2 over e plus 7 over 2. What are the questions that are out there? Brian, how are you feeling about all this? Feeling pretty good? How are you feeling?
Just some practice.
Check it.
What if we had, instead of being bounded by a function like this,
Yep.
maybe it's the
Ah! Ask that question one more time. One more time, Champion. What was the question?
instead of finding the volume like this,
Yep.
you just flip it.
Alright, so are you talking about changing the base, or I think you're thinking about changing something else?
The base.
Actually, changing the base doesn't matter that terribly much. You're gonna figure out, oh, my base looks a little different, my functions are different, my limits are different. There is a change that makes it much harder. What's the change?
I think you meant like the change of like D1. Like,
Right, it's not a matter of the base, it's the slicing that you use. Right, like this was a perpendicular to the x-axis, so dx, right, we were slicing this way. I might have you slice this way. And if you slice this way, you're going that way now? L has to be a dy kind of thing. Yeah.
wouldn't it still be like the same volume? Yeah, wouldn't it be the same volume for this one? Like, it's like you went from dx to like dy.
Not necessarily, because now you're making your squares going this way. It would look a little bit different. All right, let's just keep going. Let's play around with this.
Okay.
All right, so cross section, second perpendicular, right across these triangles. Okay. Problem number 2. I'm most interested in your ability to set this up. Just take a minute or two. Show me what you can do. Think about your base, think about your slicing, think about your volume. Alright, solid as the triangle. Is there another I can do that
Yeah.
Looks like just about everybody got their base set up. Solid as the triangle enclosed by the line x plus y equals 1. Maybe it's easier to rewrite this as y equals negative x plus 1. the x-axis, okay, x-axis, y-axis, the base. There's the base. Cross-sections perpendicular to the x-axis are right isosceles triangles. Think about your slicing. Which way? Perpendicular to the x-axis. X-axis, perpendicular to the x-axis, we're going this way. So what kind of integral?
dx.
What kind of integral if you're slicing
Oh.
this way?
dx.
It's dx, one of the easier ones. dx's are usually better than the dy's. So here we go, here's my slice. So I'm gonna call this guy here L, that's gonna be the height, the thickness, dx, delta x, whatever, Roger's not here. Let's be loose with the notation today. Okay. All right, right isosceles triangles. The right isosceles triangle, we're talking about this bad boy. Not only are they going to say right isosceles triangle, but it's the right isosceles triangle with one leg on the base. The legs in the right isosceles triangle, right, that's these guys, the two that are equal to each other. The one that's not equal is the hypotenuse. I will tell you in a BC only kind of experience, I am going to sometimes talk about the hypotenuse being on the base. But specifically the way this is defined, it says I've got a right isosceles triangle with one leg in the base. I need to think about it this way. Or if you want to imagine it going this way, I don't really care. But I need a leg in the base. So the length of a leg is what we're calling L. The thickness of the slice is what I'm calling dx. We need to do a little bit of geometric thinking over here when we start talking about slice. I'm a big fan of drawing the slice. Here's my slice. Give it a little bit of thickness. It's the right isosceles triangle. This part over here is L. This part over here is L. And the thickness is the dx. I'm curious, how would you find the volume of the slice? Right, you want to think about how do I find area of the front piece, that's area of a triangle. So it's what you were saying. It's going to be a half base times height. This is like that big B that we think about when we say volume is base times height. And then you have to multiply by the dx. So you've got a half L squared dx. Great. We've examined the base. We've examined the slice. The last thing. Right? Make the solid for me. So take a minute on your own. Show me what that setup's going to look like for the solid. From the base, to the slice, to the solid. Whoa, slow the roll. Slow the roll. So we've got the integral from 0 to 1, 1/2 L squared, the last thing I need. The last thing I need to really make some progress with this. What's L, right? What's L for this problem? This is why I really want to encourage you guys, draw the base. Get that base in there. Nathan, how long is L going to be?
1. Negative x plus 1.
It's going to be what?
Negative x plus 1.
It's just negative x plus 1. This is a top minus bottom slice, just like with area, just like with volume. So this is going to be an integral from 0 to 1, 1/2 negative x plus 1 squared dx. And if you guys don't mind, just so we can get practice with another base, I'm going to stop here. Right? Because once you get here, it's not new stuff. It's just old integration skills, and you guys are really good, but it's getting here that's important. All right, so show me what you guys can do with number, well, I'm trying to decide number 3 or number 4. Choose your point, the x-axis or semicircles.
Number 3.
He doesn't think we can do it.
Let's go number 4 with a twist.
What a twist.
With a twist.
What a twist.
Number 4 with a twist. Here it comes. Why choose between 3 and 4? Embrace the and. I hope this doesn't go badly. We're going impromptu here. Find the volume of the solid whose base is the region in the xy plane bounded by y equals x squared, y equals 8 minus x squared, and whose cross sections, no. Who wants to go perpendicular when you can go parallel to the x-axis or semicircles? I hope I didn't just make this miserable.
Wait, wouldn't it be dy?
Ah, yes, dy. dy? Poor Miss Hunter. All right, get me that base. Y equals x squared. Y equals 8 minus x squared. Okay. There's your base. And now I need cross sections. Which way are they going again? Parallel to the x-axis. So that means I'm making my slices this way. Right, as I've already heard, dy has to be dy. Okay. All sorts of stuff's about to happen. All the things, as Caroline would say.
So you're going to get me to do x by itself.
Right. With each of these, I'm going to have to solve it for x, so I can get y by itself. So y equals x squared. Well, that's the same thing as x equals the square root of y, but we're too smart. We're not going to fall for that. Plus or minus. Now, x equals the square root of y is this part of the parabola.
So what do we have to do? The secant equation the same way?
And this part over here is x equals negative the square root of y. And then you've got this parabola over here. So if you're saying y equals 8 minus x squared, y minus 8 equals negative x squared, negative y plus 8 equals x squared, I think you get x equals plus or minus the square root of negative y plus 8. Just for right now, for giggles, I want to focus on the bottom part here. Okay? So let's talk about L. How long is that slice? Think about that slice there. How long is it? Right, we're going parallel to the x-axis, so I need to be thinking to myself, not top minus bottom anymore.
Right minus left.
Right minus left. So what's L? The guy on the right
Square root of 1.
minus the guy on the left is square root of y
So what do you think
minus
be?
negative square root of y,
2 squared, yeah.
which is 2 square roots of y. Now here's the part that's going to blow your minds just a little bit. Think about that slice. What do we know about the slice?
All half of it.
Semicircles go in this way, right?
Aren't they both the same function, so you just...
Yeah, there's some cleverness that we can do here.
You can get
So take your little semicircle and draw it if you want to. I like doing it. Here's my slice. Here's my semicircle. Give it a little bit of thickness in whatever way. I can't draw.
That's a taco.
There's taco again. Okay, there's L. The thickness in this case is dy. What's the volume for the slice?
Can you get that again?
The volume for the slice.
Wait, wouldn't it be?
What do you think, Anthony?
Wouldn't it be 1/2? This equation they have here, the bottom of a solid times 1/2.
1/2 the volume of the solid.
Yeah.
Well, talk to me about this guy here.
Okay.
If I want to find the area for the base, it's 1/2 of pi r squared, right? But where's r? R is half of the thing that we're calling L. So what you really have is 1/2 of L over 2 squared dy is your volume for the slice. If you, oh wait, I think I missed something, didn't I?
Pi.
And I missed the pi. Here I need the pi.
Yay.
Yay, pi's back.
Like
Okay,
pi.
now I need volume of the solid. This is, we're just gonna set it up and we'll be done. What's the volume of that solid? Trust the instincts here. It's the same game again and again and again. You've done the hard work. You've got the slice. Get me to the solid.
Definite integral from A to
Definite
B.
integral
A to B.
from A to B. What's A and what's B?
A is the first
So
intersection.
intersection.
Not the intersections, because I'm not slicing this way anymore. I need the y values for those intersections, right? So this guy is down here at the origin. I'll tell you, just because we're running low on time, that this is the point 2, 2. Trust me, it works. So, and I'm going to be really specific with my limits of integration so that your notes make sense later. I'm going from y equals 0 to y equals 2, and now give me the inside stuff.
Oh, can I just factor out 1/4 and
Yeah, you can do that. You can do 1/2, give me L. L is this 2 square root of y over 2 squared dy. Clever stuff that you can do. 2 square roots of y divided by 2 is square root of y. Square root of y, the whole thing squared.
Y.
Y.
Why we do it?
And I forgot that. Darn
Pi.
y. So you get pi over 2, the integral from 0 to 2 y dy. So pi over 2 times 1/2 y squared from 0 to 2. Pi over 4 y squared from 0 to 2 is pi over 4. 2 squared minus pi over 4. I know I'm blocking, I'm so sorry. Pi.
Wait.
I'm not worried about that part. Here's the thing though. Pi is not the answer.
Did he pull
Oh,
out
because you have to
four?
multiply it by.
Oh,
Pi is not the answer. Why not? That's not why pi is
It's
not the
because
answer.
you only found the region for square root of y. not
All this beautiful work that we just did was to go from y equals 0
2.
to y equals 2.
So you have to multiply.
So would it be 2 pi?
Nope. Because when you go up here, now it's a different function.
Oh.
So you split it over 2 parts.
Right, you'd say go from y equals 0 to y equals 2 using this definition from L. Go from y equals 2 to, I think this is y equals 8 using the other definition for L. We're just going to play around with this tomorrow. Tonight, do as much of the homework as you can. It is not due tomorrow. But these cross sections are slipped into all 3 problems, along with some area and volume practice, which I think you guys really need.
Let's close it.
Yep, if you don't mind.